In this video, we will talk about how to find local extreme points of multivariable functions. So by local extreme points, I'm talking about local mins and local maxes. All right, so I want to begin by drawing a picture that'll help motivate what we look for when we try to find these local mins and local maxes. Okay, so I'm going to draw some axes. Okay, so let's say that I have my z-axis and my x-axis. So my x-axis, and this is my y-axis, so x, y, and z. And now I'm going to start to draw a picture of a multivariable function and what its surface looks like. So let's just say that my function looks something like this, and here it starts to kind of curve downwards like this, and then it curves downwards sort of in the back. Same thing here on this edge, starts to kind of curve downwards, and then curves downwards here, and then I won't be able to see it anymore, so I'll draw a dashed line for the back part of it. And then where this part goes down and this part goes down, they sort of connect with this hyperbola shape. And then on the back edge, this point will sort of connect with the hyperbola, and then it goes behind this sheet, so I can't see it anymore, so I'll draw a dashed line. And it's something like this. And then at a point like this right here, one of the cross sections in the x direction looks like a parabola sort of coming down like this. And of course this shape, I want this shape to sort of extend downwards forever, so it extends downwards forever, downwards forever, downwards forever this way, and then out this way forever. So it would keep going like this. And it would also keep extending this way and keep extending up. And I'm going to draw a little bit more of this shape, because so far this shape is a shape that I've seen before. It's what's called a hyperbolic paraboloid, but I'm going to draw a little bit more. I want to make it a little bit more complicated than just a basic hyperbolic paraboloid. So let's say that this portion here extended up, and then there was kind of like a high point, and then that's kind of like a high point right there. So from this high point, the graph in all of these other directions, that's the back part. I can't even see the backside. Backside, backside. And that's kind of like a high point right there. So that high point, we would call this a local max. So that's one type of local extreme point. We could have a local max. We could also have a local min if it was the bottom of a valley. We don't have any local mins here, but we have another point that I do want to classify. And the other key point that we have here is we have this point, and this is a saddle point. It's not a local min or a local max, because if I were to go in the x direction, so if I were to go in the x direction this way or that way, if I was to travel along the back, I'd be going down. That makes it seem like this saddle is kind of like a high point. But if I were to travel in the y direction, that's this way or this way, the saddle seems to be kind of a low point. So it's not a min, it's not a max. This is a saddle point. All right, so there's some key observation that I want to make a note of, and that is the following. So at a local max, a local min, or a saddle point, if the partial derivatives exist, so if fx, that partial derivative, and fy, the partial with respect to y, if those partial derivatives exist, they must be equal to 0. So the x partial derivative is going to be equal to 0, and the y partial derivative is going to be equal to 0. As long as we're at a local max, a local min, or a saddle point, and these partial derivatives exist, so I don't have anything like sort of like a sharp corner going on, those partial derivatives are going to be equal to 0. And hopefully I can see that in this picture at this local max and at the saddle point. If we were to draw the tangent line purely in the x direction at either of them, or the tangent line purely in the y direction at either of them, those tangent lines would be sort of flat. They would be parallel to the xy plane. All right. So that said, So that said, what we are going to look for when we look for local extrema, that means local mins or local maxes, and saddle points, we will look for those at points where those partial derivatives, so the partial of f with respect to x and the partial of f with respect to y, both equal 0. So that is what we're going to be looking for. All right, so next what I want to do is I want to state a definition. Okay, so I'm going to let, whoops, let's put this in black actually. I am going to let D be a determinant. So I'm going to put these sort of absolute value type bars. But this is going to be a determinant of a matrix. And it's a 2 by 2 matrix where the entries are fxx here, and then fyy there. And then on the off diagonal, it's fxy and fxy again. So if we evaluate this determinant, first we multiply these two diagonal entries. We multiply fxx with fyy, and then we subtract what we get when we multiply the other diagonal entries. So that would give us fxy squared. Okay, so this discriminant has a special name. D is called the Hessian. It's called the Hessian of f. So of my function, in this case of 2 variables, D is called the Hessian of f. But for our purposes, what I want us to know is that D is this determinant, and if we evaluate that determinant, we get fxx times fyy minus fxy squared. So where this determinant is relevant is in determining whether points are local mins, local maxes, or saddle points. And that's what the second derivative test for multivariable functions will describe for us. Okay, so what does this second derivative test say? So the preliminary conditions that we need for it is if f, the partial of f with respect to x, and the partial of f with respect to y are continuous on a disk that's centered at a point a comma b, and a comma b happens to be a point where the partial derivatives both equal 0, so the partial derivative with respect to x at a comma b equals 0, and the partial derivative of f with respect to y at the point a comma b equals 0. So a comma b needs to be one of our sort of candidates that we look for where the partials equal 0. Okay, so when we look at this point a comma b, if that Hessian, if that determinant, once we evaluated it at a comma b, is greater than 0, and if in addition the second partial derivative with respect to x both times at the point a comma b is also greater than 0, f has, it turns out, a local min. A local min at the point a comma b. If we keep that the same, for the most part, and all we change is that the second partial derivative with respect to x is now negative. So keep the determinant positive, but the second partial derivative with respect to x, make that negative, then we have a local max. If that Hessian, if this determinant is less than 0, then the second partial of f with respect to x doesn't matter. It turns out then f has a saddle point. F has a saddle point at a comma b. And the last case is, well, what if that Hessian, what if that determinant is equal to 0? When that happens, the test is inconclusive. And what that means is there could be a local max or a local min or a saddle point or none of them at the point a comma b. We just don't get any information. That's what happens if this Hessian, this determinant, ends up equaling 0. All right, so let's look at an example where we find points a comma b where these partials equal 0, and then classify them as local mins, local maxes, saddle points, or as points where the test is inconclusive. All right, so this is our first example. Find all local maxes, local mins, and saddle points of this multivariable function, f of x comma y. All right, so let's talk about how we can do this. So I want to begin by finding where the partials equal 0. So let's find the partial with respect to x. So the partial of this first y cubed term is 0, because we treat the y as a constant when we take the partial with respect to x. For 2x squared, that partial derivative is 4x. The next term would be 0, and the partial of the last term would be negative 4y. Let's also do the partial with respect to y. So the partial of the first term would be y squared. The next term would be 0, because we treat x as a constant now. The next term would be negative 4y. And then the partial, when I take the partial of negative 4xy, that'll be minus 4x. Okay, so now let's set these equal to 0. So let's set fx equal to 0, and let's set fy equal to 0. So setting fx equal to 0, we'll get 4x minus 4y equals 0. Or if I rearrange this and simplify it, this gives me that y equals x. Okay, so now if I do the same thing for fy, we're going to set y squared minus 4y minus 4x equal to 0. So at this point, what we have is we have these two equations. I have y equals x, and the second equation I have is y squared minus 4y minus 4x equals 0. So we have a system of equations. So we could use our methods from algebra class for how we solve systems of equations. So one of the things I can do is I could take one of my equations, if I have one of the variables isolated, like I do in this first equation, and I could substitute it into the other one. So let's substitute this. Let's substitute the fact that y equals x into the second equation. So doing that, y squared would become x squared, minus 4y would become minus 4x, and let's keep that last minus 4x as it is. So now I have an equation in terms of one variable. This is going to be easier to solve. So we get x squared minus 8x equals 0. And factoring an x out, we'll get x times x minus 8 equals 0. And now I can write down my answers for what x is. X is either 0 or it's 8. All right, but I need to know my y values as well, because we had two variables here, an x and a y. All right, so we need to plug these back in to one of these equations, either equation 1 or equation 2, to figure out what y would be. So if x equals 0, it definitely looks easier to plug into the first equation. If I do that, we get that y is also 0, because y is going to be the same as x. Okay, and if we do that with the other value, with x equals 8, because y equals x, that would mean y equals 8. Okay, so based off of this, we are getting 2 points. We're getting 0, 0, and 8, 8. At these 2 points, both of the partial derivatives equal 0. So if you remember back in calculus class, when we set the derivative equal to 0, and we solved, those points had a special name. They were called critical points. And that's what they're called here as well, even when we talk about multivariable functions. Except now with multivariable functions, we're going to be taking partial derivatives and wondering when are the partial derivatives equal to 0. And technically, it's also possible for them to be undefined. That also falls into the realm of a critical point. Okay, so critical points are points that are in the domain where the partials fx and fy equal 0, or at least one partial is undefined. Okay, so that's what makes a critical point for a multivariable function like this. Either all the partials have to be equal 0 at that point, or at least one of the partials has to be undefined at that point. And that point needs to be in the domain of the original function. Okay, so now that we got these critical points, we're ready to use our second derivative test. So we want to compute that determinant called Hessian, D, and fxx, the second partial derivative of f with respect to x. We want to compute these at the critical points. So we're going to need to figure out those other partial derivatives. Okay, so let me zoom it out a little bit so I can see these first partial derivatives. Okay, so I'm going to need to figure out fxx. So to do that, I look at what fx is, and that was 4x minus 4y. And I want to take the partial derivative of that with respect to x. So that's just going to be 4, because that's the partial of 4x, it's 4. And the partial of negative 4y would be 0, because we're going to treat y as a constant. We're taking the partial with respect to x again. All right, let's also do fyy. So we're going to look at the partial of f with respect to y. Let me zoom it out a little bit more. That was y squared minus 4y minus 4x. And we're going to take the partial of that with respect to y. So the partial of y squared would be 2y. The partial of negative 4y would be minus 4. And the partial of minus 4x would be 0, because we're taking the partial with respect to y. So that means we treat x as a constant. All right, and then I also, for the Hessian, I need to know fxy. So I look at fx, which is 4x minus 4y. And now I'm going to take the partial of that with respect to y, which will just give me negative 4. All right, so now that we have this, we're ready to write down that determinant, D. And remember, our formula for it was fxx times fyy minus fxy squared. So plugging in for these values, fxx is 4, fyy is 2y minus 4, and then minus fxy squared, fxy is negative 4. All right, so simplifying this, we get D equals, if I distribute the 4, we'll get 8y, and then minus 16. And then we get another minus 16, so we have 8y minus 32. So that's D. Okay, that's our Hessian, that's this determinant. All right, so what I need to do now is I need to plug in our critical points, which were 0, 0, and 8, 8, into D and into fxx. So I'm going to organize this with a table. I'll keep track of my critical point, the value of D when I plug in, and the value of fxx when I plug in. And then what the conclusion is. Let me give myself a little bit more room there. Okay, so one of our critical points is 0, 0. So when we plug that in to D, 8y minus 32, we will get 8 times, well, y is 0 at this point, minus 32, which is minus 32. So if we look at our second derivative test now, what does it say to do when D is negative? So this is condition 3. It says when D is negative, we don't even need fxx. It's a saddle point. Okay, so that's based off of condition 3. I'm sorry, fxx was not even needed because D is negative. This was not needed here. And the conclusion is, well, we have a saddle point. Saddle point because D, the Hessian, is negative. Okay, so that's what we have at one of our critical points. Let's do the other critical point. So we also have one at 8, 8. If I plug this in to D, I'd get 8 times y, and my y value is 8, minus 32. So this is 64 minus 32, which is positive 32. All right, so what does the second derivative test say to do when my value of D is positive? So that could be either case 1 or case 2. In both of those, D is positive. What we need to know is, what is the value of fxx now? Is it positive, like case 1, or negative, like case 2? Okay, so I need to plug in my critical point into fxx, but fxx is a constant, it's just 4. Okay, so that's nice. That makes it easier. So what does the second derivative test say happens when d is positive and fxx is positive? That's case 1, and it says, oh, local min. So local min, let's write that in. Local min. All right, so I just need to write down a sentence now that says my conclusion about what's happening at our critical points. So by the second derivative test, f has a saddle point. It has a saddle point at 0, 0, and a local min at 8, 8. And that's our answer. All right, in terms of our goals for this section, we've now discussed how we apply this second derivative test to determine whether our critical points are local mins, local maxes, or saddle points, or sometimes how the second derivative test can be inconclusive when our determinant is 0. All right, so in this video we focused on local mins and local maxes. In the next video we'll talk about how to find absolute mins and absolute maxes of multivariable functions on what are called closed and bounded regions.